Wait. All right, now go. Hi, everybody. My name is Jeremy. I was a student at CU, and now I just work as a navigator and outreach presenter doing planetarium shows. Everything you'll be seeing today is going to be live. Rémy will be giving you a lot of the information, and I'll be controlling the system remotely from the comfort of my own home. So hope you guys enjoy some of the cool things we have to talk about with you today. Nope, let's get into it. Uh-oh, we can hear Jeremy, can't hear Rémy. Let me make sure here. What about now? Rémy, do you have some sound?
Can everyone hear me?
Uh-oh, technical difficulties, please stand by.
Is it working now? Okay, I believe you can hear me now.
Okay,
I see a lot of yeses. Live show, everyone. So
still working out the details, but okay.
We're working on it.
Now that everybody can hear us.
Let's go again. Hello and welcome. Time number 2 to Fiske Planetarium's Dome to Home series. This is our first ever live stream public show, in case that wasn't obvious, and we're really excited to share this with all of you. So just a little introduction. We already got to know Jeremy down there, but my name is Rémy. I'm an astronomy student at CU Boulder, and I work as a live presenter for Fiske Planetarium, both in the Dome and for outreach. I'll be doing a lot of the talking here today, but clearly Jeremy's going to have to do some of it in case that sound goes down again, but we should be good. So we are thrilled to kick off the series, which will run for the next few weeks while Fiske is closed. So a few logistics. What's really neat about having this as a live program is not only that you get to be here for our technical difficulties, but you get to interact with us and we get to interact with you. So if you have a question, either submit it in the link below or type it in the live chat window, which is in one of these directions below me. So we have our question master and chat moderator, Amanda. She's behind the scenes looking out for questions, and she'll relay them to us to answer. So try to keep the chat a little bit relevant, but if you want to ensure that we are doing a good job and it's fine that sound went off, feel free. So I think that just about covers it, unless I forgot anything, Jeremy?
Nope, it sounds good.
Okay, excellent. So this week's topic is patterns in the solar system, which may sound familiar from the title of this video. And that means that we get to tell you about patterns in, get this, the solar system. So let's start simple though. Let's go ahead and go outside. I remember outside. Feels like so long ago. Jeremy's here to remind us what the outside looks like. I haven't seen the sun in a while. So here we are. We're looking south. And to give us this added sense of realism, we're here in this field. So astronomy began by cataloging motions in the sky, working them out to predict future motions, figuring out why those motions are even happening in the first place. And the best way to look at the motions of the sky is to look at the entire sky. So instead of just looking south, let's go ahead and lay down and look at the whole sky. So here we are. Now you can see the entire sky. Like we said, this is dome to home. So this is our dome, and that's your home. Get it? And please note the cardinal directions here. South is below us. We got north above, And your east and west might be backwards than you expected. We've got west over here and east over there. And that's because we are looking up, not down on a map. So keep that in mind. So anyways, let's start by cataloging the easiest motion in the sky to see. That would be the sun. So here's the sun, 4 p.m., April 17th, 2020, from Boulder, Colorado, where we are streaming from. So I'm willing to bet that y'all have heard of the concept of day and night, though I know I personally have lost track of when those are lately. But day and night do in fact happen. That's just when is the sun up, when is it down, caused by the Earth spinning. So this is probably the easiest pattern to notice. But it's more than just sun up and sundown. You may have noticed also that summer days are longer than winter days. That's what makes summer summer and winter winter, hot in the summer, cold in the winter. A neat little pattern for you. And it's a really common misconception that this pattern is because the Earth is closer to the sun in the summer. But there are a few issues with that explanation. So first, let's look at where the sun is in the sky during different times of the year.
Alrighty, so those lines that I've brought up, hopefully everybody can see a red, green, and a blue line. They mark the paths that the sun will excuse me, the path that the sun will take through the sky on those specific dates.
So you can see there, June solstice, that's summer solstice, longest day of the year, the sun is up higher. And then during the winter, December, the winter solstice, shortest day of the year, it's not up high at all. So with the sun being higher or lower in the sky, our idea of it being closer or further from the sun being the cause of the seasons doesn't make a lot of sense. Another issue with that idea is that summer isn't summer everywhere. So we're getting into summer up here in the northern hemisphere, but down in the southern hemisphere, they're getting into winter. So if this were just a matter of how close we are to the sun, that wouldn't make a lot of sense. There's also that the Earth's orbit, it's not a perfect circle, sure, but the difference in distance between it being the closest and the furthest is only about 3 million miles, which sounds like a lot, but the average is about 93 million miles. So it's not too much of an issue there. So the real cause for the seasons is the tilt of the Earth, because the Earth isn't oriented straight up and down compared to the sun. It is actually tilted about 23.5 degrees. So there are times where we're tilted toward the sun and times where we're tilted away from the sun. So that means that we're either getting more direct sunlight in the summer during that June solstice right there, or less direct and less sunlight during the winter with that December solstice there. Congratulations, we've learned. But we're getting close to sunset. The sun's not the only pattern that we've got. So let's take a look at patterns in the nighttime. We've got our fancy dome here that can fast forward time. This isn't going to be real time. You don't have to sit there listening to me for hours on end while we wait for the sunset. So just as we're going there, note that, again, these stars that we're going to see are the ones that we're seeing tonight. For those watching right now, that's tonight. For those watching later, it's April 17th, 2020, specifically in Boulder, Colorado. So if you're not in Boulder and you're not tonight, then you're going to see a different sky. But here we are. So it's tough to notice unless you know stars very well, but the stars do also move and they change. It's wild fact. It's really exciting. But again, this is because the Earth is spinning. But that motion is a little bit different from the motion of the sun, though. We know that the sun rises in the east, sets in the west. Cool. That's mostly true for stars as well, but there's a little bit more to them because they're everywhere in the sky. They're not just in that one spot. So we can make that a little bit easier to see. Jeremy, if you will.
Right, so now what I've done is I've just turned on any type of trail marking the path that these stars are taking throughout the sky.
That does, in fact, help. Thank you so much. So as you can see, stars aren't just rising and setting. They are actually twirling around. So you'll notice that they're twirling around a specific point, and some of you might be able to guess what it is. And here's a hint. You can see the directions again. To the north. If you guessed the North Star, congratulations. You have some bragging rights. If you did not, then you were here to learn anyways, so no worries. So it's actually a pretty easy star to find too. if we want to turn off the trails and take a look.
All right, so if many, or one of the more wide-known constellations, American constellations, is of course the Big Dipper, which is located right about there. And the Big Dipper can be used to find Polaris. If you follow my mouse here, and you use these two pointer stars on the, I guess, the spoon end of the dipper, and follow them in a line that goes right to Polaris. So if you're ever lost and looking for the North Star, you find the Big Dipper, find the pointer stars, and extend those into a line right to Polaris. Many people think that the North Star, the Polaris, is the brightest star in the nighttime sky, but it's important to note that it is definitely not. It is a bright star, but it is not one of the brightest, or not the brightest. Great. Once we're at Polaris, if you want to do a little bit more of a tour of the nighttime sky, Polaris is actually the tail end of the Little Dipper, located right there. So you can find two quick, easy constellations in the nighttime sky.
Awesome. So yeah, there's Polaris. We call it the North Star because it really is always in the north. And it'll be higher or lower in the sky depending on how far north you are, but you can always find north by finding that. If you are in the southern hemisphere, I am so sorry, but you cannot see this star. You can find south, but there's no star there, so it's tougher. The reason we have a point that it's spinning around, that we have this star, is that our North Pole is directly pointed towards Polaris, which makes it the North Star. So it's the thing that stays fixed in the sky because that is the direction that we stay fixed in the sky. Again, South Pole isn't pointed toward anything. I am so sorry.
But they have the Magellanic Clouds to look at in the southern hemisphere. So you know what? You gotta make some trade-offs, right?
You gotta make some trade-offs. So as we're going through time here, which is excellent because it would be really boring to stay here all night watching me on YouTube. We've got another pattern that's coming up right over there in the eastern sky. You can see it. Wow, it's the moon. You might have heard of the moon before. You might be acquainted with it. You may have seen it recently. And yes, Jeremy, zoom and enhance. So you may have also noticed about the moon that it goes through phases. And we've got our handy chart here. Awesome. So you can see that the moon is currently in that waning crescent phase. So waning means that it's getting less full and the crescent is less than half of it is lit up. If it's more than half full, it's a gibbous. And if it's getting more full, then it is waxing. You've got your wax on, wane off. So you've also may have heard full is when it's completely lit up, new moon, it's dark. So then the question arises, how do the phases happen? We've got our awesome pattern, we've cataloged it, we can guess when the moon is gonna be in whatever phase it is, but why does it happen? And the best way to get a sense of why the moon has phases is from space. So let's go ahead and take a look from space. Awesome. Bye, Earth. Or hi, Earth, it comes. There you go. So first off, the moon's large enough that we can see it, but it's still pretty far away. In fact, the moon is so far away that you can fit every single planet in between the Earth and the moon, but it is still our closest neighbor. So we need to figure out what our moon pattern, what causes it there. And we know first off that the moon is not glow in the dark. It's not shining on its own. And Amanda says that we've got a question. So let's take a look here. We've got someone who asks, why is the moon in the same plane as the planets? So all of the planets and everything, we're going to talk about this a little bit later, all are on the same plane here. So we go all around, the ecliptic is what it's called, where the sun is. So the moon is part of the Earth system, so it's going around in the same plane. So let's take a look here. We've got the full moon right here, as in the entirety of the moon, not the actual full moon. And we want to know why we only see part of it lit up. And that would be the day-night cycle on the moon, actually, because the light on the moon is coming from the sun and the moon does go around. So let's go ahead and, Jeremy, could we pull up our fancy moon cam, which will show us what the moon looks like from Earth as it goes around.
Ooh, sorry, I need to shrink down the moon again to its actual size. There we go.
Too powerful. There we go. So we can see here, we're not seeing much the moon lit up right now, but as it comes around and it's opposite of the sun, we start seeing a full moon. So that's all about day and night on the moon. And it takes about an entire month to go all the way around.
1 month?
1 month, that works. And that's why our lunar cycle is about a month or month. And you may also see here that we're always looking at the same side of the moon. So we're always looking at the same part of the moon. And there's a good reason why that happens. Let's get rid of the moon cam and make the moon and Earth a little bit bigger so we can watch why that is.
All right, there's a much bigger moon here. And I'll enlarge the Earth a little bit too, just so you know what you're looking at.
So you can see here that the moon is in fact spinning, but it's spinning in the exact same amount of time it takes to go all the way around the Earth. So the moon rotates exactly once per orbit around the Earth. That's called tidal locking, and it means that we only see that one side. And it gives us a far side of the moon, but not a dark side of the moon. So,
it's also important to note too that it might look like the Earth is not spinning right now, but that's just because of the way that I have centered the system right now. In fact, the Earth is actually spinning.
The Earth is in fact spinning. You heard it here first, folks.
You heard it from dome to home.
Absolutely. Tell your friends and family. So, we're way out here in space. Let's take a look at some other solar system patterns. In fact, let's actually use some solar system patterns to solve a problem. And the problem that we want to solve today is, how was the solar system made? So no one was actually there when it happened, so we can't just ask around and find who was there and they can tell us. We have to look at these patterns that we see and come up with explanations that make sense for them. So there are a lot of patterns to find. We'll take a look at them. We'll see what might make sense, and then we can confirm or throw out theories based on other patterns that we see or more evidence we find. And that's really how science works when you really boil it down. Explain something, either find out it's right, awesome job, or that it's totally wrong. Oops, try again. So let's look at some patterns out here in the solar system. So we've got our nice side view here. Thank you, Jeremy. And we can see, I think the easiest pattern to notice from out here is that it's pretty much along the same plane like I was talking about before. So it's pretty flat, what's happening there. Everything's orbiting around the same plane. There's not a lot that's happening above or below there. And so that's our first idea of what might have happened. So whatever idea that we come up with, we got to make sure that it leads to this flat solar system. So we'll log that as clue number 1. Write it down in your handy dandy notebook. And let's take a look maybe from another angle and see what other sorts of patterns we can pull up.
Spin us around so we can get a top-down view of our solar system here.
Awesome, thank you. And actually, could you make the planets a little bit bigger?
Sure.
Awesome. So all the circles you're seeing are the orbits of those planets, which is cool. You can see that they're nearly perfect circles here, but we want to see how the planets might be moving. So we're going to make them bigger. They are not actually this big. And yeah, let's make time go fairly fast so that we can see here. It would really not be great if we were doing this in real time, just sit here on this live stream for hundreds of years while we wait for planets like Neptune to go all the way around. So our handy time machine. And we can see here that all of these planets are orbiting in the same direction. So that's another thing to log away. So we've got flat, they're going in the same direction. And you can also see that the further away the planet is from the sun, the slower that it is going. So that's another nice motion pattern, but there are more patterns than just how something is moving. So we can take a look at the planets themselves. So let's think for a moment. We've got our inner planets that are close to the sun, Mercury, Venus, Earth, and Mars. And these are all rocky planets. We also call them terrestrial planets. They're rocky, they've got a surface, we don't fall through the Earth. And then meanwhile, our outer planets are Jupiter, Saturn, Uranus, and Neptune. And those are gassy planets. They don't have a surface. You would just keep falling until you are crushed. So the reason for this is that heavier elements, the rocky stuff, not the gases, they have an easier time surviving the heat that comes from being so close to the sun. Then out further away, it's cold enough that things like gases and hydrogen, helium, ammonia, things like that can come together more easily and form these larger gas giant planets. So again, whatever idea we come up with for how the solar system is made, we have to make sure that all of these facts, all of these patterns fit into them. So let's take a look and see how they might all work together. So all these facts, mostly flat plane, orbiting the same direction, speed of the planets, they play a huge part in our concept of how the solar system was formed. Essentially, what happens is that there's this huge cloud of gas and dust, mostly made of hydrogen, but a bunch of other stuff, all the other things that we see in our solar system, and it started collapsing due to gravity. That's how gravity works. It's an attractive force between things. So it starts collapsing, and as it collapses, as it contracts, it starts spinning. So everything kind of has a spin, and as it contracts, it spins faster and faster. It's the same way that if you watch an ice skater, if their arms are out really far, they're spinning but not very fast. The second they pull them in, they start going really, really, really fast. So that's what happened with the solar system. As it got smaller and smaller and smaller and contracted more, the faster it spins. And that's how you end up with these spinning planets. And they're all going the same direction because they were all made from that same cloud. Cool. So that's one thing there, but then how did it flatten out? That's some really neat physics there that you can actually see. Have you ever seen those videos of people making pizza? Or maybe you're cooler than me and have made pizza yourself, where you've got that big ball of dough and you throw it up in the air and they spin it around and it starts flattening out? That's what happened here. So this whole spinning cloud makes a lot of sense for getting it to flatten out as well. So as it keeps contracting and collapsing, the center of what we call the solar nebula because it's a cloud, solar because there's going to be a sun there, that center eventually becomes a star. When the core is hot enough, start fusing hydrogen. But if you want to learn more about stars, definitely come back on May 13th for our full show all about stars and the sun. So while that core, which was about 99% of the mass of the cloud, as it contracts, the outer parts start coming together to start forming planets. So it's just the outer bits start coming together to form planets. And we can actually see theories like this in action. We've taken pictures of solar systems far, far away, or forming solar systems. Ooh, like that one. Thank you, Jeremy. And pictures like this do seem to confirm our idea. So there is a question. Here we go. So is the theory that all the planets formed at the same time, courtesy of Denise? Hi, Mom. So planets all form basically together around the same time, but by the same time, we mean over the course of millions of years. That's how astronomy works. When we say something happened quick, we're like, oh, it was a pretty quick process. It only took a few million years. That's how it is. So we've got our idea about how this was all made, and all the evidence that we see really confirms that. So, you know, those pictures that we see far away confirm our idea. Looking at the way the patterns work in the solar system confirms this idea. But as we get this far out, and as I'm talking about these really nice patterns, this is where people start going like, hey, what about all of our exceptions? What about Pluto? This is immediately everyone asks, what about Pluto? So Pluto is a bit of an exception, yeah. So we have everything here in this nice plane, but then we've got Pluto that's not really adhering to our pattern. And there's always going to be exceptions to our nice, pretty patterns, but we can't immediately throw out our theories and explanations until we know whether or not we can explain exceptions like this. And Pluto is one of the exceptions that we can explain. So here you go, you can see it's wonky orbit. I'm pretty sure that's the scientific term, wonky. And the way that we can explain it, so Pluto is actually one of a lot of objects that are out there past Neptune. They're called Kuiper Belt objects because, surprise, it's an object and it's in the Kuiper Belt, which is that region past Neptune with Kuiper Belt objects in it. So all these things have fairly wonky orbits. Ooh, these are other dwarf planets that we have, and then these are other Kuiper Belt objects. And they all have these kind of wonky orbits. And that's thanks to gravitational interactions with larger bodies that end up kind of flinging them into a weirder orbit. So it's always smaller things that you see in these odd orbits. When you get larger things like the planets, they're all on that nice flat plane. But smaller things like Kuiper Belt objects and comets end up with these weird orbits. So even with exceptions like this, we do still feel confident in our model of the formation of the solar system. So, which is to say that even simple patterns can lead to some really big and amazing ideas, like this concept that a giant cloud of gas just came together, started spinning, and made our solar system. Just by looking at the way that these planets move, we can come up with theories like this. So let's take a look here. I think we've got time for some questions here. So if anybody has a question about anything that I talked about, throw it in the chat, and we do have some questions that were pre-submitted. So while I wait for all you curious people to throw up some really neat questions for me, I'll take some of those older ones. So we've got Moon Cow from Boulder who asked for more about planetarium culture. Ooh, so like who makes the shows? Are they locally made or are they produced? And then astronomy versus the music shows. So that's really exciting. So there are a lot of planetariums and production companies that make the planetarium films that we show. And we happen to be one of them, though a lot of our films that we feature were also produced in other production houses. We do make some of our own, and you can find them on the website. Our planetarium is really unique, though, in that aside from just showing these films, we also have a live presenter like me who's there to give a presentation and answer questions. And we're also really unique because most of our staff are actually university students or were recently university students like Jeremy down there. And that's really exciting that we all get to be involved in something really cool like this. So, and then as far as music shows versus astronomy shows, the astronomy shows are all our educational stuff. The music shows, which are really cool, students put playlists together, and then navigators like Jeremy also create and plan out the visuals that go with them, and they're totally live. They're exciting. Come by when Fiske is open again for an astronomy show or music show. That would be amazing. We've got a question in the chat here from Shelly. Talk a little bit more about tidal locking. Yeah, so there are a number of like systems that are tidally locked, and our moon is one of them. It's about gravity kind of pulling them back, and it ends up that one side of one of the bodies is just facing it, and it's the same size or the same side all the way around. So with the moon, we have one side of the moon that's always facing us, but with something like Pluto and its moon Charon, it's the same side for both of them. So you have the same side facing each other. If you're on the opposite side of Pluto, you're never going to see Charon. If you're on the opposite side of Charon, you're never going to see Pluto. All of the largest moons of Jupiter, the Galilean moons, are also tidally locked like that. It's really, really common, actually. We have...
Here's an image of Pluto and Charon, Rémy.
Yes, awesome. There they are. They're looking great. Pluto and Charon. Pictures from the New Horizons mission in 2015 with our nice little heart on Pluto. So it's always the same side of Pluto that's facing Charon and always the same side of Charon facing Pluto. And that's tidal locking. So our next question from MC was planet requirements. Yes, so there are 3 requirements for being a planet. The first one's pretty obvious. Orbits the sun. Cool. The second one is that it's roughly spherical. So it's they're not always, or they're not a perfect sphere. They tend to bulge a little on the side, again, like making the pizza. It spins around like that. But they're roughly spherical. It's not some lumpy potato-looking asteroid. And then the third one is that it has to have cleared its path all the way around the solar system there, or all the way around the sun. So it's like the most gravitationally dominant object in its path. I've got Aris right here, who wants to know, why are the North Pole and Polaris aligned? Did Polaris just happen to be that way? Yes, it's totally a coincidence. It's amazing. It just happened to be that way. That's why there's no South Pole star. And actually, the Earth does kind of wobble. So in a really long time from now, like thousands of years from now, it'll be pointing at a different star and come back around. And that's how that goes. We've got Billy Bob Joe here, who wants to know how many dwarf planets there are. Currently, there are 5 recognized dwarf planets. We've got Ceres in the asteroid belt. We've got Pluto. We've got Haumea. We've got Makemake and Eris. So the thing about dwarf planets is they don't dominate their region of space, but there's enough gravity to be a sphere, and that's what makes a dwarf planet. And that's why Pluto's a dwarf planet and not a major planet anymore. I'm so sorry. All right.
Let's see.
Have we got any other questions here?
What happens first? Earth is a pancake from orbiting, or sun swallows Earth?
Earth is a pancake from orbiting. The person who asked that the Earth is a pancake from orbiting, do you mean that the spinning kind of flattens it out? Because if I'm going to take it as, do you mean, is the Earth going to flatten out from the spinning, or is the sun going to swallow us first? So first off, there's enough gravity with the Earth that it's going to stay together. It's not going to pancake out. So definitely the sun will engulf us first, but it's not going to quite engulf us, actually. It's going to expand into what's called a red giant. And again, if you want to learn more about stars, that's definitely May 13th, come for that, and you'll learn more about what happens with stars. And it's going to expand out, not quite engulf the Earth, in about 5 billion years. So keep an eye out. I need to be able to hear Jeremy.
Was it confusing for early astronomers to have the stars move? How accurate are early star charts? That is a great question.
That is a great question from MC. So stars are actually really predictable because stars in our sky don't move around on their own terribly much. That has to do with them being so far away. So if you're standing here and you move your head like this and like this, your hand moves a lot. If you're looking really, really, really far away, something far away doesn't move as much. And that's how stars are. Even as we move around the sun, they don't move very much. So knowing where stars are is really, really easy. So those were pretty simple. Some of them have changed a little bit. For example, Sirius, which is a star that's kind of close, has drifted pretty noticeably in, just thousands of years, which is the blink of an eye in astronomy. Planets, though, were really challenging. It was really figuring out the planets that was tough. Stars, super predictable. Planets, since we're moving and planets are moving and we're roughly close, we end up getting not just planets going across the sky, but they also do these kind of loop-de-loops. That's called retrograde motion. That's when one of the planets overtakes the other one in the orbit because it's going faster. In the same way that if you're passing a car on the road, it kind of looks like, oh, that car is going slower than me. In fact, it's maybe gone backwards, but it's still going forwards. That's what happened there. But back in the day, to try explaining these by saying that they were orbiting around the Earth and were doing these spins as they did so. They managed to be able to predict where they would be pretty well, but not for any reason that was true. But to come back around, it wasn't terribly difficult to figure out where the stars are going to be.
Looks like we have the next question from Billy Bob Joe. How do we know how long how do we know how long it takes for a planet to orbit if some take hundreds of years?
Yes, so that's a matter of tracking how long it takes to go from point to point and then doing the math from there. It's a lot of math. So although you can clock how long it takes a car to go all the way around a racetrack, you can also clock how fast the car is going and see what's the racetrack going to look like and how long is it going to take at the speed that it's going. So for example, Uranus takes 84 years to go around the sun. And that's something that did not take 84 years to find out, because we could find out what its path is and find out how fast it's moving along that path. Thank you. We've got about 5 minutes here, so any other questions, pop them in the chat quick as possible and we'll get to them. Ooh, while we're waiting on that, here what Jeremy has pulled up on the Earth, you can see the glowing green lights up there. Those are the northern lights, or the aurora, and those are caused by charged particles from the sun coming into Earth's magnetic field and just lighting up in the north.
Amanda, question master, do we have any other submitted questions on any of the forums?
Oh. So we've got a question. Over here in the chat, there's a question, which phase is our moon in right now? So the moon is currently in that waning crescent phase. You might recall from earlier. That was from Denise, thank you. You might remember a few days ago, or maybe like a week or so ago, there was that full moon. It was like that super moon, really, really bright. But it's come back around and it's a waning crescent now. And in just a little while here, it'll be new again. And last call for questions. Otherwise, we're going to go ahead and call it a day. Let's call it a day. Yeah, it was really great to be here. Really loved talking with you. Enjoyed your questions. I hope you learned something and had a good time. Thank you so much for coming. Yeah, we really appreciate it. So next week, just so you know, we're going to be back here Friday, 4 p.m. Tara and Parker will be celebrating Earth Day all week, and they'll be talking about Earth's place in the solar system and how it relates to life and our atmosphere. They'll also take a look at Venus and Mars as well to find out why they're so different and why Earth is the perfect place for life. And they'll even take a look at planets outside our solar system. So thanks again for joining us today, and don't forget to like this video and subscribe to our YouTube channel for more videos like this. So from all of us here at Fiske, thank you so much and have a great week.
Thanks, everybody.